this video what we're going to do is look at a few more examples of how you would measure the standard electrode potential, so the tendency of a particular half cell to push or pull on electrons through that circuit. And we're going to look at ones where both species in the half cell this time are aqueous ions. So here's a few examples of some half equations where there are no solid metals. We've got tin 4 plus ions and tin 2 plus ions, iron 3 plus ions and iron 2 plus ions, dichromate and chromium 3, and then manganate and manganese 2. Now these half equations just contain solutions, so there's no metals in there. And our half cell has to contain both of these oxidised and reduced species. So in this example it would be that one and that's the oxidised and reduced species, this and this, this and this, this and this, but must all be in that beaker together. Now interestingly the bottom two don't work without the acid, so we have to put that in the beaker as well. We don't need to add extra water because they're all in solution, so we don't need to worry about the water. Basically, pretty much everything in the half equation has to be in the beaker. The electrons, remember, are going to go through the wire, and because we're using solutions, water is already there. So basically we need to make sure everything is in our beaker. And because we have no metals, we're going to use that platinum unreacted electrode again to get the electrons out of the cell. So if we were doing the Fe3 plus Fe2 plus, we can copy down the equation from above. We've got Fe3 plus Aq being reduced to Fe2 plus. If we were being asked to measure how much of a push or pull this has, we would measure it against hydrogen. So just pause the video and see if you can label the left-hand side only of this diagram. Okay, so the left-hand side is our standard hydrogen half cell, so it's the same labelling we've been doing up until this point. And remember that if we're measuring standard electrode potential, then we will always have hydrogen on the left. And then on our right-hand side, we've got to put our iron 2, iron 3 half cell. Now, because neither of those things is made of metal, then our electrode is going to be made of platinum. And our solution is going to be 1 mole per decimetre cubed Fe3 plus and 1 mole per decimetre cubed Fe2 plus. So we're getting an equal amount of each of these two things, both at 1 mole per decimetre cubed. So they both need to be at that concentration. Now if you get asked for the name of the solution, you will have to come up with the name of a solution that contains those ions. My top tip for you is always come up with the name of nitrates, because nitrates are always soluble, they don't make any precipitates, and so you know that they'll always be in solution, whereas silver chloride is a solid, barium sulfate is a solid, so some things are not in solution, but nitrates always are. So if I had to come up with them, maybe just name a nitrate, so say iron 3 nitrate or iron 2 nitrate. What you find when you set this up is that to get a positive reading on your voltmeter, the platinum of the iron half cell, so the platinum of the one we've drawn on the right, is the positive, is connected to the red wire, which means that it's a positive electrode, which means that it is actually a value of plus 77 compared to hydrogen, it's more positive, and electrons are going to flow from the platinum of the hydrogen to the platinum of the iron half cell. Okay, so they're going from the hydrogen half cell to the iron half cell. How would we do our conventional representation for this one then? So remember we put the salt bridge in the middle, and the left-hand side is going to be our hydrogen one, which we have H plus and H2, phase boundary. Right. We know that we need to connect a crocodile clip at the end, so we put platinum. Then out of iron 2 and iron 3, which one's highest? Well, iron 3, and then iron 2. And we don't need a vertical line there, do we? Because iron 3 and iron 2 are both aqueous, so we just put a comma. But then you can't connect an electrode to that, so we put a line and platinum, And that is the end of our conventional representation. So let's look at this second example. If we just copy down the half equation from the previous page, like that, can you label up the two beakers? So have a go at seeing if you can label up the two beakers. So in this example, the left-hand side is the same as it's been all the other times. The just thing to watch out for is, in order to get the half equation to work, you do need the acid in the right-hand beaker as well. So we've actually got three things. Remember, it's everything up here except the water, because the water is already there. When you set this up, again, you'll notice that the manganate half cell is the positive terminal. So you have its positive compared to hydrogen, which if it's reading 1.51 volts means that that is a plus 1.51 volts E0 value. And remember, electrons flow to the positive, so they're going to flow from our hydrogen half cell, the platinum on the left, to the manganate half cell on the right. And can we draw our conventional representation? So remember, double lines, the left-hand side we should be pretty good at by now. Remembering that we have to be able to connect the crocodile clip at the end. Out of these things though in our beaker, and we're looking at the manganate and the manganese, which one's the highest oxidation state? So you need to be careful, it's not just the charge on the iron, it's the oxidation state of the manganese, and in MnO4- it's plus 7, whereas in Mn2+ it's plus 2. Now MnO4- needs to be acidified, so we're going to put the acid in brackets with it, and then we get Mn2+. So we've got acidified manganate turns into Mn2+. So we put a little bracket round acidified manganate because they were on the left of the arrow together, and then a comma to separate it from Mn2+ because they're the same phase, and then a line to separate that from platinum because platinum's a different phase, but we can connect our two platinum electrodes via a wire. So our final type of these that we're going to have a look at is one where one of the things in our half cell is a gas this time. So our equation, Cl2 gas plus 2 electrons. We were trying to turn Cl into Cl-. That's our reduction. What's the value for that and how would we measure it? So remember that if we're measuring standard electrode potentials, the left-hand side is the standard hydrogen half cell. So pause the video and fill in the labels for the left. So that's the left-hand side. Now our right-hand side is the cell we're trying to measure. So we've got chlorine gas and chloride ions. So ions are in solution. So we've got our Cl- AQ here. Remember, we want 1 mole per decimetre cubed of that. But chlorine is a gas, so it has to go in via one of these little gas chimneys, and it has to go in at 100 kilopascals. Remember, we have to put those standard conditions in there. Neither of these two things is a solid metal, so we're going to use our inert platinum electrode again. And when you set this one up, the voltmeter reads 1.36, and the chlorine is connected to the positive terminal again. So this is a positive electrode, and so the value is plus 1.36 volts for chlorine. Now electrons always flow to the positive, so electrons are going to flow from the hydrogen half cell, the platinum of the hydrogen half cell, to the chlorine half cell, the platinum of the chlorine half cell. Remember that they flow to the metal, the platinum bit. So what was our conventional representation? Salt bridge in the middle, hydrogen half cell we should be getting good at by now. Right hand side, who's the highest oxidation state, Cl2 or Cl-? The Cl2 is 0, Cl- is -1. One of those is gas and one is AQ, so a phase boundary. You can't connect electrode to the chloride ion, so you have the platinum electrode there, which is a solid, so we have another phase boundary.